And we're starting. Hello and welcome to another wonderful adventure of New York City Category Theory Seminar. We're running a little bit late and I apologize for that. Today we're having Michael Lesnick talk about limit commutations via minimal initial functors. Take it away.
All right, well, first, thank you for the invitation. Thank you all for being here, both in person and remotely. I work in the field of applied topology, topological data analysis, and I'm going to tell you about some work on a sort of foundational computational problem in category theory that arose through this topological data analysis work. And this is joint work with Tamal Dey at Purdue University. The work was completed.
You have to click on the slides too.
Yeah, I will in a second. Thank you. The work was completed in early this year, and the paper is available on the archive. So I thought I'd begin with an introduction to topological data analysis. So this is a field that uses old and well-developed tools from topology and abstract algebra to study the shape of data, the coarse scale, global geometric features of data. For example, things like clusters, loops in data, or tendrils in data. And the field has its origins in works from the 1980s and 1980s to 90s of several authors, and even before that, some people trace the origins back to the work of Morse, for example. But around the turn of the millennium, there started to be a real interest in this field, and people have been working on these things very actively for like the last quarter of a century. So TDA has grown into a major research area with a very well-developed and I think nice theory, a lot of efficient software, and hundreds of applications. A colleague of mine, Barbara Giotti, actually maintains a database of applications of TDA to engineering the sciences called DONA. So at a high level, here's what TDA is. We are given a data set and we construct a diagram of topological spaces from the data. That is some functor valued in topological spaces. Maybe it's valued in simplest complexes if we care about computation. And then we analyze the topology of this diagram and hope to learn something about the data. And oftentimes, most often, we're using homology with field coefficients so that we can work in the computationally friendly realm of linear algebra. Most often, this diagram is filtration, a one-parameter filtration. There's a growing sequence of topological spaces like this. And this is the setting in which we define persistent homology, the flagship tool of TDA. This provides invariants of data called barcodes. Let me quickly explain this to you. This is not what my talk is about, but this is context because I want to try to motivate the category theory stuff that comes later. So say we have a data set like this. We can, well, we want to use topology to study this, but it has no topology. It's just it's the discrete topological space. So we thicken it somehow, and then we get well, the thickening depends on a scale. So thickening at different scales gives you a filtered family of topological spaces. But this particular construction is called the Vietoris-Rich construction. You choose a scale, you connect points by edges that are within distance that scale, and then you take a clique complex on that. You add all other higher simplicities that you can.
Right, so it's a way of taking a metric space and converting it into a step-little compactor.
Yep, that's right. And so again, this isn't really the focus of the talk, but that's what I'm showing you here. Now, if you apply homology with coefficients in a fixed field to each simplicial complex and each inclusion map, you get a line-shaped diagram of vector spaces, a sequence of vector spaces and linear maps like that. And then it turns out that you can apply structure theorem to this, basically some variant of the structure theorem for finitely generated modules over a PID. And this tells you that the isomorphism type of this object is completely described by a collection of intervals or equivalently pairs of indices in this sequence. We call that a barcode. Okay, that's like TDA 101. Now, a lot of my research focus is on an extension of this called multi-parameter persistent homology, which has become a very mainstream topic in TDA research in the last few years. And this arises in the study of data with outliers, where the construction that I just showed you is very unstable. The one parameter construction, it arises in the study of dynamic data. It arises in a lot of places. And the idea is to construct a multi-parameter filtration from data in order to capture more structure. So for, in the last slide, we looked at a one parameter filtration, but you could also look at a two parameter filtration where you have a grid's worth of spaces and things are getting bigger in each of the coordinate directions. So for example, in the construction that we saw over here, the so-called Viator-Rips construction, we can extend that to a two-parameter construction by filtering the data by density. Put a density function on the data somehow, and then that gives you a second parameter. And we keep only the densest stuff. That depends on the threshold. You change the threshold. That's another filtration direction. There's a lot of different ways to do this. I could give a whole talk about the many different.
And you take homology of all of them, and they all fit together?
Yep, you apply homology to the diagram. Now you get a diagram of vector spaces of the same shape. Okay, but I was going to say, I'm not going to give that talk. That's a different talk. Right, so we're not going to go into the details of the many different ways.
But the point is that to do the same homological algebra with a multi-parameter filtration, it all works out.
Well, let's see.
Oh, not quite.
This, and this work out. Now, what about this last arrow? Well, turns out that the homology of an n-parameter filtration, this n-parameter diagram of vector spaces, has wild representation type if and only if n is greater than 1. Okay, without going into the details of what wild representation type means, and this is a classical notion from representation theory of quivers, but basically it means that the set of the space of indecomposables that can arise in these algebraic objects is enormously complicated and nasty. It's like really nasty. And because of that, details omitted, but there's no nice definition of barcode in an n-parameter setting when n is greater than 1. And that's something I could make precise if I wanted to. I won't here.
Can you go back for a second and just, because my short-term memory is gone, I understood everything before, and you mentioned what a barcode is, but tell me again.
No problem. Okay.
So
So
you get you take homology along the thing, and then how do you get the barcode in the regular case?
by a standard structure theorem or a variant of some very classical structure theorem in abstract algebra. I said it was a variant of the fundamental theorem for finitely generated modules over a PID.
Think of the persistence module as a representation. The barcodes are the indecomposables.
Yeah, another viewpoint on it is that it's known that certain quivers are of finite type, and any quiver representation decomposes in a really nice, simple way. Okay, that's another viewpoint on the same classical idea.
I remember, if I remember intuitive ideas, that when we look at homology, the barcode tells me that when I get to a certain filtration, maybe a certain cycle appears, it stays for certain values and then may disappear again.
Exactly. Yeah. Thanks for mentioning that. I would have liked to mention
Hence
that.
the
if I
word
remembered.
persistent.
Yeah. So for example, here you see this big cycle appear. This is the most salient topological feature of this little data set, right? So then, and this cycle is present, and intuitively it's still present here as well, and then it closes up here. So that's going to be witnessed by a longer interval. The first persistent homology barcode here is literally this in this example. You have one interval for this small cycle and another one for this bigger cycle that appears.
So by that standard construction, you mean the adjoint functor, or how do you go from a sequence of homology groups to the barcode?
It's a structure theorem, right? It's an analog of the structure theorem for finitely generated abelian groups.
So homology is a functor. So we don't just have the sequence of vector spaces, we also have linear maps everywhere, right? Which is how we get to the.
And so this
We can view this as a representation of a PID. That's the classical, most classical way to get to the decomposition theorem. We can view it as a representation of a finite quiver of type A, and something depending on what you're actually doing. We can view it as a representation of the total order of the reals. And for all of these, there are nice decomposition theorems. The PIDs is essentially undergraduate algebra. And all of these decomposition theorems end up with a description where you get these pointwise one-dimensional indecomposables that are completely described by when they first show up and when they go away.
But they never go away.
Well,
They
you have
It's
a-
called then with a cell.
Closes up.
I see.
because we're in a quotient module.
Just getting back to that barcode, would it be fair to say that this barcode is sort of analogous to a Fourier transform or something like that?
I don't
So-
I don't know about any analogy of that of that kind. This is like a isomorphism invariance. It's a simple
Yeah,
bit of numerical data that completely describes the isomorphism type of the object. And I don't know if I would think about Fourier transform in those terms, but maybe there's an analogy that I don't see. In any case, I have to tell you guys that this like has nothing to do with the content of my talk. It's just background for the background.
No, it's understandable. We like it. I mean, I like it.
well, we like background.
We like background.
Good.
Examples make everything much easier to write.
Okay, thank you for. I'm happy that you're taking something good out of it. And so now let's continue though. Okay, so there's no nice barcode here. That's also we could give a whole talk about what you can and can't do in terms of barcodes in this setting. There's some interesting things to say that we won't. But in short, there is no nice barcode in this multi-parameter setting. And so what we want is simple computable invariants of these homology diagrams that can serve as a surrogate for the barcode. There are many ideas for this out there. A lot of people have had different proposals. One way that's relevant to this talk is to do the following. You take your diagram, you restrict it to some nice you take the indexing poset and you restrict it to something, and then you take limits and colimits. Okay, that's one thing you can do. I'll say a bit more about that. That's something people in TDA have been considering, and that brings me to what this talk is actually about, which is the following problem. Compute the limit or colimit of a diagram of vector spaces. Okay, very basic problem, right? So basic that I'm almost surprised that I would have anything to say about it, but I do. Okay, so specifically, I'm going to look at finite posets or posets that are intervals in n to the d, in which case it don't require finiteness. Just wait to find out what that is, please. Things are well known about this, and probably for a category theory seminar, you know about this. But first, a limit of a diagram of vector spaces can be computed by solving a linear system by equalizer formulae that you can find in McLean's book, right? So like stuff from the beginning of category theory. And also, we can sometimes simplify the computation by restricting along an initial functor. So if the initial functor has a source with fewer objects or morphisms, you'll get a smaller linear algebra problem to solve.
So we say initial, mean initial to the whole category or
What does initial mean? It means for everything here, there's one before it. Or-
Something like that. I will define initial.
oh,
Okay, but it's like some condition that
or for every
guarantees that
two,
you.
for every two, there's one. No, that's directed or something.
It is a condition that guarantees that you preserve limits.
The limit will be the same, I know, but yeah,
Yeah.
it's actually equivalent to that. Yeah.
Exactly.
Yeah.
Okay, so although these things are very well known, it seems to us that their computational algorithmic implications, including some structural things, have not been worked out before. And that's the contribution of this work. So we're going to study how to optimally choose the initial function here. All right. Maybe move this, please.
Yeah. Okay.
Oh, sorry. I didn't realize that I had control over that. I'm happy to do it myself.
That's okay.
Thanks. Let me see if I can. I'm just gonna like shove it off.
Oh, yeah,
this
that's
side.
perfect.
Okay.
Can I just say, these
Yeah.
initial functors have something to do with calculating cloud extensions. Is that true?
That's a good question. Is there a?
Okay, anyways, you're gonna explain.
I don't know any description of this in terms of con extensions. So my answer is to my knowledge, no, but
Well,
I'm not a category theorist, by the way. There's a lot I don't know. So let me continue though. So this is like the abstract of the talk, okay? So first, we're gonna show that there exists a minimal initial functor f from P to our poset Q. And minimal here means one where the sets of objects and morphisms are both as small as possible. Okay. Second, we give an explicit description of all such f up to isomorphism. We also give algorithms to compute them, and the algorithm depends on which of these cases we're in. Then if for Q a finite poset, I don't have anything interesting to say about size of these, but if Q is an interval in ND, again, we're promised a definition of that soon, we're going to bound the size of P in terms of the number of minima of Q. So we can say non-trivial things about the size by making connections with commutative algebra. And this all yields new algorithms and bounds for computing limits. And then there's a TDA application, which I'll talk a little bit more about. Okay, so now preliminaries. I don't know this audience. Some of the things I have here are like really basic.
Assume we know nothing.
Okay.
I like that.
Okay, so fine, I will. Okay, so a poset is a
Okay.
pair where the first element is a set, the second element is a binary relation. It satisfies three nice properties: reflexivity, antisymmetry, transitivity. And I'll just denote the pair by Q.
Say, how important is anti-symmetry in all of this?
Important. Yeah, I wouldn't be able to, like, if I didn't go for my results.
It's a poset, not a pre-order.
Well, what I say at the end of my talk is that I think all of this probably can be extended to arbitrary finite categories, but I haven't done that yet, and neither is Tamal. So yes, I really need it to be a poset. And so is it true that if I only drop this, then I get a pre-order?
Yeah.
Oh, then it doesn't matter. Just like choose a skeletal.
Yeah.
I don't know, like just choose one representative of every equivalence class. It should be fine. So
I don't want to do that either, but anyway. Never mind.
for my problem,
Then there might be more bookkeeping.
if I understand correctly. Okay, so
Actually, less.
let's continue. Right. So the point of this slide is that in my setting, you can represent posets by Hasse diagrams, directed graphs. So a poset Q is locally finite if for any pair of elements, the set of stuff between them is finite. And if Q is locally finite, it's determined by its Hasse diagram. This is the directed graph. Vertex set is Q, and you have an directed edge XY for every unfactorable relation XY. Okay, so for example, let ND be the poset with a product partial order, namely x less than or equal to y, if and only if the ith component of x is less than or equal to the ith component of y, for all y. And then its Hasse diagram in the d equals 2 case, well, in general, it's a grid, and in the d equals 2 case, part of it looks like that. And now, I promised to tell you about intervals. So Q we'll say is connected, my poset, if it's non-empty. And that's really important here, that I make this is a convention that connected means non-empty. And any pair of elements x and y and q is connected by a zigzag of relations. All right. And then for Q locally finite, Q is connected if and only if its Hasse diagram is connected. So this aligns with your geometric intuition about connectivity. And now let's assume that Q is embedded in an ambient poset, like Q be, let Z be n to the D. Then we call the subset Q convex if Y is in Q whenever X is less than or y equals, X is less than Y, Y is less than Z, and both X and Z are in Q. So this is like the natural poset theoretic analog of convexity. And we'll say an interval in Z is a connected convex subset. For example, something like drawn in yellow here. All right, some people in the community, the TDA community, don't like the word interval. They think it means something else, and they'll call it.
Well, and this already shows some, like you were saying earlier, if you have intervals in 1D, they're only going to be things with endpoints as opposed to here where there could be much more complicated objects.
Exactly. Some people want an interval in this generality to have a least endpoint and a most endpoint, but not me.
Yeah.
I don't know what has happened here. Why is my slide?
Oh, it says okay here. You have to go here. Press okay.
Thank you.
Okay, sorry.
No problem. Thanks so much. Okay, so all right, now this slide doesn't really have a lot of content, but it basically says we're going to regard a poset Q as a category. Elements are objects, order relations are morphisms, like usual, if you're in that world. And we're interested in computing limits of functors f from Q to vec, where vec is a category of finite dimensional vector spaces over a fixed field. So this is, if your Q is this, then your diagram of vector spaces looks like that. And now again, I don't know if I'm supposed to do this, but like I have a definition of limit here. So a cone, and it's just for the case of vector spaces, but a cone on F from Q to vec is a vector space V, together with maps from V to all the vector spaces of F, such that everything in sight commutes like that. And then the limit of F is a universal cone, specifically a terminal cone, by which I mean for any other cone whose vector space is V prime, you get a unique linear map from V prime to V, such that this commutes with everything. Yeah, so that's a limit. And now important for computation is to acknowledge that there's a concrete description of limits, which is classical. So I'll use this language. A section of F from Q to vec is just an element of the product of all the vector spaces. And that just means we choose a vector Vx for each vector space Fx, such that for each x and y, you take this vector and you map it forward by the structure map and you get Vy, right? So I should have said, like, this just means that these choices are compatible with the structure maps. Okay, and then the classical result is that the limit of F is the space of sections of F where the cone maps are projections. And now, if we're working with a finite poset, we can kind of give a little bit more, I guess, concise description, or we can construct the limit in a sort of more tidy way by basically just considering the product over the set of minima. So let M for the rest of the talk be the set of minima of my poset Q, and then limit of F is the collection of vectors V in the product over the vector spaces just over the minima, so that if you take two minima and you have some guy above them and you map the vectors at these two minima forward, then they go to the same thing. Okay, so it's like another analogous compatibility condition. But the point is, you don't need to take the product over everybody, just over the minima, and you can still construct the limit. And then your cone maps are a composition of projection onto the factors with the structure map.
So this would be just because if you know the vector at the minimum, it uniquely determines every other vector.
Exactly. So what I'm saying is very basic.
Okay.
Okay, and so
Well, every vector that lies above it.
Yeah. Right.
exactly. So okay, so look, this is a linear system, right? So now this shows that you can express the limit as the kernel of a matrix, and you can say what its size is. I mean, it follows essentially from what's here. And duly, you can compute the colimit as a kernel. In other words, like the same machinery that computes the limit here, just transpose some stuff and it will also compute the colimits.
Well, of course, in the category of vector space, it's self-dual, right? So,
Right.
I mean, vector opposite is vector, so.
Right. Yes. Okay, so
And Florian says this is all duality. This dualizes, that's important.
yes, it's duality. It's nothing more, nothing less.
Yes.
So now, so just here's an example to make this concrete. I mean, I don't know how obvious this is to everybody. Again, I don't know you guys, but so I follow Nosum's advice and say more rather than less. So we consider a functor where the poset has this shape here. Then according to the thing from the last slide, the limit of F can be seen as a subspace of the product of these four vector spaces, right? So you've got a vector space VA and FA, and similarly for these other minima. And then we require that VA and VC map to the same spot under this map, and VC, VE, VF all map to the same thing under here, right? So you get that's expressed by these equations. Now here's a variant of this example, and this is going to motivate initial functors. So now I've added a terminal object here, and we've got arrows in the Hasse diagram coming up like that. And then according to the last slide, we get some more equations. For example, like we require that FA maps to the same thing as FC when you go forward to FG, right? But what I want to tell you, and maybe if you're familiar with these things, you know what's coming. This last line of equations is actually redundant. Okay?
Yeah.
And that's because this square is commutative and these maps factor through here. So like, yeah, it's the last line of equations is redundant, and the formalism of initial functors sort of systematizes this idea in a very abstract way. So now we come to what you guys asked about before. What are initial functors? Well, I'm just going to define them for the target being a poset, just because that's convenient for me, but all of this is fully general. So for a functor E from C to Q with C small and X an object of Q, the comma category, or an element of Q, the comma category E down arrow X is the full subcategory of C with objects W such that EW is less than or equal to X. Okay? And then we say E is initial simply if for each X in Q, this comma category E down arrow X is connected. Okay, so in particular it has to be non-empty. So let's see that play out in an example. Here's this little poset from before, and I give you a subposet in blue, right? And so let's look at this vertex here. So I claim that the inclusion here is initial. So let's at least just check for one vertex. Okay. So because this is an inclusion, I'm just looking at the downset of this vertex of the intersection of this downset with P. Right? That is this little, what do you call them? Coast bands? You guys are the category theory experts. This little 3-term zigzag is this comma category. Do you see? Okay. Is that connected?
Which dot is X?
What?
Which dot is your X? That's your X.
Yeah. Sorry, I don't know if this completely doesn't work.
No, that's fine. No, it's fine. That's fine. Just that's the X. Okay.
Yeah. Sorry to the people online. If you couldn't see me point, you probably could have.
Oh,
Okay. So below this is just this little 3-term thing here. That's connected, right? And if you check every single point here, you'll see that they're all connected. Okay. So that's an example of an initial functor. Proposition standard. If E is initial, then for any f from Q, the vec, the induced map on limits, which you have by universality, is an isomorphism. And again, that doesn't require this to be vec. That's just my setting. Okay. So now the question arises, okay, initial functors, you see that like replaces a bigger limit computation with a smaller one here, but how do you algorithmically choose an initial functor? That's what we're after. And so now a little detour, finishing my discussion of TDA motivation, if I may, just maybe 2-3 more slides. So the TDA folks have been interested in this thing defined in terms of limits and colimits called the generalized rank. So given f from Q to vec with Q connected, we have a map from the limit of f to colimit of f, and it's given by just choosing any object in Q. You look at the cone map from limit f to the vector space there, and then the co-cone map into colimit of f, compose them, and by connectivity, it doesn't matter which object it shows.
That's true for any category. Nothing to do with vectors.
Yep. Yeah, I mean, a lot of what I'm saying, maybe now is a good time to tell you something that I forgot to say, which is like the main ideas of this work, like they're all on the source side. They don't care whether but like
Well, to define the rank.
yeah, but I mean as far as like the applications of generalized rank, which is like something we do. Yes, it works for vector spaces, but like the main ideas about initial functors, like anywhere where they don't care that much about the source category. And in principle, you could use them just as well for any target category where you can compute stuff.
For that matter, attaching significance to the limit to colimit morphism is also independent of what category we happen to be in. The rank happens to be a very useful invariant barcode-like in its simplicity for the case when we're working in vect. But this diagram being interesting also should be very widely applicable.
That's a nice observation. That's true. Yeah. Importantly, the map itself is canonical, right? So, all right. In any case, so this quantity has a nice representation theoretic interpretation, which maybe justifies its consideration. It's the number of interval summands of f with support Q. So what is an interval summand? That's a diagram of vector spaces where all the spaces are the field and all the maps are the identity map. Okay.
So you're saying like the diagram in this case might not be representable as a sum of just the barcode pieces, but like there will be some barcode pieces in it. Is that what you're saying?
Yeah, I mean I'm saying something related to that, but slightly different. Let's look at a picture to understand this. So say that could have gone
Watch
a
out
lot
for your
worse.
brain.
That was my most lucky moment of the day. Now, okay, see this? Imagine a diagram of vector spaces where at every dot you had your field, okay?
Mhm.
And at every edge you had an identity. This generalized rank counts in an arbitrary diagram, the generalized rank counts the number of summands of that form.
Mhm.
And that form only.
That form for this entire diagram, or are we looking for?
For the entire diagram. So if you want to
So
see
if I
the sub-diagram,
have some zeros and some fields, that's not counted.
Yeah,
Okay.
that's right.
Interesting.
And this is kind of the first published version of this result that I know of is here, but it's like been folklore for a long time. I think people have known this. So, okay. In any case, TDA people like this. And so there's been a bunch of papers that consider what's called the generalized rank invariant of one of these multi-parameter diagrams of vector spaces where you what it is you just restrict to different intervals Q. You choose an interval Q, you restrict the diagram to Q, you take the generalized rank of that, and then like you just consider the whole pot of these different Qs. That's a huge invariant, but it's theoretically interesting. And I won't really fully get into it, but it's equivalent to some kind of generalized notion of barcode where intervals can take positive and negative multiplicities. Again, another talk. But in the case D equals 2, there's a software grill by my collaborator Tamal Dey on this that on my work that uses part of this invariant. It's too big to use all of it, but it uses part of the invariant as a feature for machine learning and does reasonably, I think. And so, okay, this is being used in TDA for some kind of data thing. We'd also like to be able to do this for D equals 3, but here's the thing. So for computing intervals, to be able to do that, you need to be able to compute these guys, right? So for intervals in N2, work by Tamal Dey and co-authors showed that generalized rank can be computed by a TDA technique called zigzag persistence. Never mind what it is, but they have a good method for doing this, and that's what Brill uses for those machine learning computations. Yeah.
Yeah, sorry for some of my questions, but but the interval is like the barcode is multiple like pairs of numbers, right? But this is like one number. Is that right?
It's many
General.
numbers because you're going to restrict it to different subintervals Q.
For every Q, I get a number. So does this strictly generalize the barcode?
It does.
Okay. Thanks.
But it's very big, which is problematic. But then you can just take some simplest parts of it and do something.
Now, if you go to a case of 1 with a barcode, what would this invariant boil down to in that case?
What was that?
If you just went down to case of 1 dimension, ordinary thing where you have barcodes, what would this invariant boil
It
down
would
to?
boil down to the barcode that I talked about at the beginning of the
Sure.
talk.
I see. How would that be expressed as one of these things?
You would have to take a certain Mobius inversion.
Okay.
That's one way to think about
Okay.
it.
All right.
So, okay, so now, okay, so Tamal Dey and his collaborator Shin generalized this, also using some zigzag stuff to compute generalized ranks over arbitrary posets. Okay, and now I can tell you how this project started, because otherwise I wouldn't have started working on this. Which is that Tamal, who's kind of a friend of mine, who we've talked about math a lot in the past. When he finished this work, he reached out to me and said, you have a background in algebraic stuff. Like, let's talk. I want to tell you about this thing that we've done and let you know what I think. And what I thought was, after we talked about it, you have like this very novel methodology to compute these limit to colimit maps, but like classical category theory also has these tools for computing these kinds of things that we just talked about. So why not use those, right? And so that's how I started working with Tamal on this. And I said I think it should work just as well to just use this classical stuff. But then when we started to think about that, we realized that like if you wanted to use all the efficiency afforded by initial functors, technology was missing. So that's why we started doing this. Okay, and eventually found out that after too long, we found out that even if you don't use initial functors, the classical method is more efficient. So that was like a really long lead up to actually being able to tell you what we did. I don't even know how much time I have left. How are we doing?
You have a half hour.
Okay, that's more than I need. So now we go on to explaining the contribution. So I start off by explaining the structure theorem that I mentioned about these minimal initial functors. So, okay, suppose I'm given a poset with finite downsets. I'm going to define a subposet. I'll call it IQ, and this is the set of all elements. And it's probably better to just call this a subset. It says subposet, but I think it should say subset. Never mind. So X is this is the set of all elements in Q whose open downset is disconnected. Okay, disconnected. If it's empty, it's disconnected. Yeah. So note that the set of minima of Q is contained in IQ because the set of minima is the set of all elements of Q whose open downset is empty. All right, so now let's look at an example of this IQ. Here's my same poset from before. All the minima are in there. And the other 2 points that are in there are this and this. Why? Well, here he is. Oh, what is open downset? I should have told you. In case it's not clear, I mean the downset, but without X itself. Right? So his open downset just consists of these 2 points. No edges. That's disconnected. His open downset consists of this, this, and that. These two are connected by an edge. He's on his own. That's disconnected. Okay?
Is this IQ capturing exactly the sites where you have a generator or a first layer relation?
I guess so.
So the
I mean, I don't know
the
what
Morodian Colson's first multi-persistence paper introduced Tor-based invariants that get you the generators and several layers of higher CCGs.
I understand what you're asking, and the answer is yes, and that will come in a moment.
Okay.
You're right. So just a definition that will be convenient for the remark that follows. A subposet P and Q will say is initial if the inclusion is an initial functor. And now, so what I want to tell you is that this gives you like a first pass solution to the minimality problem, because as a full subposet of Q, IQ is initial, and also any initial full subposet of Q contains IQ. Okay, so this is the smallest initial full subposet. That's cool, I guess. But it turns out you can do better because we can often remove relations while preserving initiality. And that leads us to the main construction, which is the following. What happened? Oh, this is what the full subposet looks like, the arrow up here. So this is what we call an initial scaffold. So an initial scaffold of Q is a subposet P in Q whose object set is IQ from before, but there'll be fewer relations in general. So for each X and IQ and component, this is a bit technical, but each component A of the open downset of X and Q, P contains exactly one relation, M less than X, with M in A. And because of transitivity, necessarily M is going to be a minimum. Okay, so I'll just say it again because that's probably a lot, right? Like you have a point in IQ. If it's a minimum, it has no downset, but otherwise it may have a downset. And like over here, say like this point, you look at each component. So there was this component like that and this component, and for each you take one minimum in the component and you get to choose it. Here you have no choice. You would choose this and you would choose that. Okay, but in general you have a choice. So Q can have multiple initial scaffolds, but all by construction have the same number of elements and relations. For instance, the poset here in orange has 3 different initial scaffolds. Okay, and they all contain this little M on the bottom and this edge on the right. But then there's going to be a vertex from one of these minima of the M to the top, and you can choose that. It can be, or rather an edge. You can choose it like that, or like that, or like that. So you have a choice. Okay, and all of these, the next theorem tells you are these are your choices of minimal initial functor.
Because of the connectivity of the downset, whatever you pick then propagates across the rest.
Yeah.
Yeah.
Maybe this gives you a formal answer to.
Probably.
So, okay, so as a reminder, an initial functor f from c to d is minimal for any other. The other has at least as many objects and at least as many morphisms. Or like the cardinality is greater than or equal to. And for the structure theorem I'm about to give, I'll say that f is an embedding if it's an injection on both objects and morphisms. I guess that's standard, but I thought I'd define.
And home C here is the disjoint union over all home sets.
Yep. And okay, so now here's our structure theorem. I think for the category theorists, this is probably the most important slide. And so suppose that Q has finite downsets. Then first there exists an initial scaffold P of Q, that's a triviality. And the other two are not trivialities. The inclusion of the initial scaffold into Q is initial and minimal. So it is a minimal initial functor. And this is all of them up to isomorphism in the following sense. At least if IQ is finite, then any minimal initial functor f from C to Q is an initial scaffold up to isomorphism. And the way that I chose to express that on this slide is that it's an embedding and its image is an initial scaffold. Okay, so I've completely described the minimal initial functors, but wait, I'm supposed to look at finite posets and intervals in n to the d, but it turns out that this IQ is finite whenever Q is an integral in n to the d, so this result actually does apply in that setting. Okay, so now we know what these are. It's supposed to be motivated by computation, so we now worry about size and computation. But do you guys have any questions?
Can you say anything about when all the initial functors that aren't minimal but have like smaller cardinality than D, right? Because it looks like you're saying, oh, we found all the minimal initial functors. It would also be interesting if you knew all of the initial functors such that, you know, the cardinality of C is smaller, right?
Yeah, no, I don't know about that. That's like of course a bigger space of objects. I don't have any, I've never thought about that, but that's interesting. Okay, shall I go on? Okay. All right, so I will talk about size of initial scaffolds now, and I'm going to quantify this relative to the number of minima. So this example shows that an initial scaffold can be arbitrarily large compared to the number of minima. In this example, the initial scaffold is the poset itself. There's two minima, but there's many vertices, right? Or like many elements. So for finite posets, I don't have anything interesting to say. But in the case of intervals, I do. I think I may have already told you. So for P, an initial scaffold of an interval Q in n to the d, the size of P, including the order relations, satisfies the following. Size of P is theta of size of the theta of the number of minima if d is less than or equal to 3, theta of the number of minima squared if d is greater than 3. I don't know if you guys know this notation, but like there's a big O notation that all mathematicians should know. And this is just like a tight version of that where you have a lower bound and upper bound. Okay, it's common in computer science. So, okay, the most interesting case of this by far, in my opinion, is the case d equals 3. It is really not obvious a priori that this should be, the size of this object would be linear in the number of minima for d equals 3. For d equals 2, it's kind of obvious. Like, I mean, you look at this picture, like you're just kind of zigzag down the bottom of the staircase. That's the whole story. That should be linear. But in d equals 3, you have these intervals like in 3 dimensions. That's interesting to me. But maybe to a commutative algebraist it's trivial. But in any case, the proof uses classical results about Betty numbers of monomial ideals. It uses stuff from commutative algebra. And yeah, this was fun to make this connection. I'm not going to go into it too much because there's already a lot of stuff in this talk. But basically, well, maybe I will go through some of this. Let's see. So for you, the upset of the interval Q and ND, we have that the upset is you just take everything above. You have that the set IQ is contained in IU, and that's strict in general. But this IU is exactly the support of a monomial ideal. Don't make me define monomial ideal. But now there's standard results that count. So basically, this reduces the problem to counting the size of Betty numbers of by Hotcher's formula, there's a result that says that this is the union of the support of the 0th and first degraded Betty numbers. Okay, so you can like apply some commutative algebra without too much work. See, you're basically counting Betty numbers of monomial ideals here.
Okay, I won't ask because you didn't.
So, okay, but then that's a problem that's been well studied. Like mathematicians have loved Betty numbers of monomial ideals. So you have bounds of this in terms of the number of I-dimensional faces of a convex polytope. Okay, so there's this reduction due to their Piva-Sternfels from the late 90s. But then that's useful because there's this classical result in convex geometry that tells you bounds on the number of faces of a convex polytope. This is the upper bound theorem of McMullen, which some of you guys may have seen. It's a famous theorem. And so then all this basically gives you bounds on the Betty numbers of the monomial ideals, and so gives you bounds on your size of the IQ. Okay, and that's pretty much. And then finally, the open down set of any I and Q in the setting has at most D components. So you don't get anything more from the relations. I don't know, maybe that was too much more detail. Too much detail. Maybe I should have followed my initial instinct and not gone through it. But the point is, like, you get to get this result without too much pain by.
I very much appreciate the detail level you're at now.
Oh, thank you. Okay, it was worth it then.
Right, so the upshot of all this is that theta of m on the previous slide.
Yes.
Yeah, I mean all these bounds, but it's
Right.
particularly this most interesting case.
Okay.
Right. Yeah, because the bounds on the number of with Betty counts for ideals in n to the 3 for monomial ideals is linear. That's the point.
Okay.
Right, and that's a kind of classical.
Uh-huh.
So, all right. So then,
So I see. So you're related to this, yes, known facts from commutative algebra.
and this was exactly the intuition that you had that it's kind of the same thing.
My bachelor and master's thesis in Stockholm was specifically on generating functions for Betty numbers of monomial ideal.
Oh, neat. Okay,
So this has echoes for me.
that's pretty cool. Okay, thanks for telling me that. So, all right. So now about computation. So there's computation in the case of just finite posets, general finite posets, and then computation for intervals, and we handle them pretty differently. For finite posets, the result that we have is pretty straightforward. I mean, like the proof is given a Hasse diagram VE of Q, we can compute an initial scaffold in time O of number of vertices times number of edges, and then like we use depth first search. Okay, details omitted. Like there's no real insight that goes into this, but we couldn't think of how to do it better. More interesting is computing initial scaffolds of intervals in Z to D and Z to the D. And the reason this is more interesting is like you might have a very big poset. It could be infinite, right? But nevertheless, it's going to be described by a finite amount of information. And so the first question is how do you encode such an interval? And I think the right way to do it, if you want to allow for infinite intervals, is like this. You write Q as so Q is the interval. You write Q as the set theoretic difference of its upset and another upset. This is illustrated here. So here's Q, right? Its upset is, well, part of its upset that I'm willing to draw is here. And then you take Q out of its upset, you get this other upset, okay? So Q is fully specified by its minima, which are the same as the minima of its upset, and then the minimum of this other complement upset. Okay, so that, and I'm going to call the size of those collections of minima S. And then we can compute an initial scaffold of Q in z to the d in the following times. O of s log s if d is equal to 2 or 3. Again, the interesting case is d equals 3, where we actually have to do a lot of work. Not deep work, but it's like 6 pages of like technical crap we had to do. And O of s to the fourth for d greater than or equal to 4. By a somewhat simpler argument. It could be that this improves. Like it might be you can do better if d is equal to 4, for example.
My immediate reaction to every single s log s that I see in the wild is this because of sorting?
Yeah, I think so. But I can tell you what we do.
Hmm.
I mean, at a high level. So first, we observe that if you're going to be able to solve the problem just for an upset, you're going to be able to solve it for an interval. So most of the work is just solving this for an upset. And then we you're in 3D, we go slice by slice and iteratively find the Betty numbers. Slice is basically what it is, but getting the details right is annoying. I'm not happy to have to write that up. But we did. So, okay, so then computing limits, right? This is supposed to be a talk about computing limits, so there should be some payoff. And this paper has I think it has a nugget of cool stuff that I like. Like I really like that structure theorem that I shared with you. But then to finish the story, there was a lot of annoying stuff. The paper's 46 pages, and a lot of that is well, how should you actually represent the diagram of vector spaces? And then depending on different choices, you have to do different things to address the limit computation. So that was the part we had to do, but so I'm just giving you the simplest version of that. So assume that f from Q to vec is represented by a matrix for each structure map. Okay, that's not really a realistic assumption in TDA. Usually you have a presentation or something, but it's the cleanest for me to just assume I have every structure map given to me completely. Okay, and then I let D be the maximum over that IQ of the dimensions of these spaces. D is maximum dimension, roughly. And then I have a limit computation result for general finite posets and one for these intervals. So for Q a finite poset and P an initial scaffold of Q, I can compute the limit in time V of V times E. That's the time to compute the initial scaffold plus size of P times the number of minima squared times D cubed. Okay, some technical result, but
Who's D?
maximum dimension.
Oh, maximum dimension.
Okay, you only need it over this initial scaffold. Yes. And then, okay, but all this, to be clear, all of this is we have some content about computing initial scaffolds, and then we just apply the standard equalizer formula that is in McLean's book. Or actually this variant for minima, but same thing more or less. Okay, and then for an interval Q and Z to the D, we can compute limit of F in time O of S times D cubed if D is equal to 2 or 3, and O of S to the fourth D to the cube if D is greater than or equal to 3.
So for asking who's little s here, who's s here?
S is the size of this representation of the poset by taking the upset and then the complement and looking at the minimum.
Thank you.
Yeah, I'm surprised that the difference is so stark in computing an initial scaffold and not very stark in computing the entirety of the map. There's for the initial scaffold, we're comparing s to the fourth to s log s. In this theorem, it's s cubed d cubed versus s fourth d cubed.
Right, I think it's because the algebra itself is expensive. All this linear algebra to compute ranks, or whatever, on big matrices is expensive.
Will you be able to replace some of the cubes here with the matrix multiplication?
Yes, I've written it like this for simplicity. So that is.
It's not so terrible. I mean, the D is equal to 2 to 3. It's S to the 3, S to the 3 D3. He took it out of the parentheses a bit.
No, I'm surprised that the difference is so much smaller here.
Well,
Then it
you
goes
have
on the
an S
previous
cubed
slide.
as opposed to an S log S in the previous thing.
Yeah,
Right. But that's because, again, you gotta, we don't have, so actually, I mean, I have things to say about everything that just came up. This is actually my last slide. So first, as you asked, we can give better bounds in terms of the exponent of matrix multiplication, and we write it that way in the paper. I just thought it just makes things more annoying. And like, I don't know, if you're gonna, we didn't implement this, but if you did, you're not gonna like use Strasson's algorithm or something. So, second, similar bounds hold for limit or limit to colimit computation, details omitted, but it like goes the way you expect. Also, I did say this before, somewhat, but F is usually given by a presentation in TDA, or more generally, implicitly as the homology of a chain complex of free modules. And that's where I said we had to do a lot of annoying stuff to like check that these bounds, just to like write down the bounds in that case. So we do that. In the D, if you were working in this homology of a chain complex setting, then in the D equals 2 case, you can actually refine. What can you do? I think you can refine this bound. And look, you get corresponding refinements for limit to colimit computation. And so once you do the refinement, you recover some very slight improvement of the result that Dey, Kim, and Mamoli had. So we're really in the 2-parameter case. So we're really kind of vastly extending what they did and like situating it in like a more like proper category theoretic setting. Like you get this from computing limits, full limits. And so lastly, I already said this, but I think the most interesting theoretical question that comes out of this for me is, well, we already had to work pretty hard to do this for posets, but I don't see why, I don't know how to do it, but I think it should work for arbitrary finite categories if you pin down the right definitions. So I think that would be kind of cool to eliminate that restriction. And then lastly, applications. And so let me close by giving you a confessional, which is this work is weird for me because I mostly work in TDA stuff. And when I do TDA projects, I'm usually very confident about like the role that they play in the development of like some corner of the field. Whereas here, like the application, the story I told you was fine, but I didn't work on it because of that. I worked on it because like this cool foundational question came up from talking to Tamal. And yet, so I think it's good somehow, but like I don't know who gives a crap about it. So like I'm hoping somebody will. And that's kind of like, I mean, outside, specifically, like maybe there's something outside of TDA. And that's how we got in touch in the first place. But I was like writing some emails around. So if you know what the heck this could be good for in the world, please tell me.
one direction I would be interested in seeing someone look is initial and terminal algebras turn up in functional programming for the various functors that show up in functional programming as container data types. And the initial and terminal algebras of these functors in turn give you useful things to work with corresponding containers, and even gives you algorithms for handling these container data types. I wonder whether this notion of initiality matches the one in the functional programming setting, and whether these give us something useful for that.
That's interesting. Of course, there's also this conflicting use. I think it's conflicting. You guys can tell me. Like this other use of initial, like initial object in terms.
Well, that's when I was first when I heard the word initial when I walked in here on your first slide.
Yeah, like I don't know that that's an instance of this. Right, but
No.
but then there's also varying terminology around this. Like this used to be called cofinal, but people don't like that. So okay.
So, but applications you can do to your persistent homology theory. I mean, that's what the story you told us in the beginning. Now you have a good way of using your double filtration, or no?
Yeah, no, this is the motivation that we're giving, and there's nothing wrong with that. Like I like
Well, I
that
mean, for
story.
example, the guy who did the zigzags, do they think that could help them with what they're doing? That you showed that a computer program or a computer thing using zigzags.
Yeah, I mean we improved on that.
So it did it. Okay, well, that's okay. So you,
that story would have
Yes.
been changed. So I think I think the reason we're interested in speaking here is because you already know you've solved this to TDA. You want to see if anyone else cares.
Yeah, yeah, exactly. It's more like, here's this thing, like it seems very foundational, like aren't limits important? Like if they're important, like can somebody want to compute them? So like here's at least in like a broad class of examples, a better way to compute them than what we had. So like, does anybody care?
Well, I guess
It's like
another
that.
question you could ask is, even saying you would category vector space, it maybe takes sense like vector space on a Abelian category or something. Maybe some of the things, that you wrote specifically might work more generally.
Yeah, maybe. But yeah, if you have any ideas in that.
Just an obvious thought, like you said, because some of the definitions there were some things that were specific, like we mentioned the rank, but then there were other things. So, for example, you have the construction of the graph and the initial thing. Well, maybe that didn't use too many facts about vector spaces. You might have your whatever those minimal things, or I forget what you called them. The things you found might exist more, even if the target category wasn't vector space.
It had nothing to do with the target category. It's just a construction on the source.
Okay, so then that's already quite a general. Yeah, that's okay then.
But where do you plan on publishing this 50-page paper, 46 page paper?
Wherever we'll take it.
That's the right answer.
We spent a lot of time thinking about that, yeah.
So, but that's to a category theory journal.
If somebody had told me that we should definitely submit it to a category theory journal, we might have, but we've already submitted it somewhere. We submitted it to Foundations of Computational Mathematics. So if you see down the road that it gets submitted somewhere else, and you know what happened there.
Yeah, I was just because you're kind of asking, I would say theories and applications of categories, TAC, compositionality, both of those would definitely be interested in this work.
Yeah.
The applied category theory community in general would definitely be interested in this.
Yeah, thanks for those suggestions. Yeah, depending on the paper was submitted a good couple of months ago, but if they don't take it, then yeah, we'll be back to that discussion. Those might be really good options. Thank you.
Any more questions? Any questions from online?
I have questions. I'm very, very interested in that slide with the proof sketch. If we could talk more about that.
Sure, happy to.
So for an upset of Q, then you take I of Q. What is I of Q again?
So I of Q is this set that I defined. Where is it? Over here. It's just a set of all elements of Q whose open down set is disconnected.
Okay.
Tell me when to scroll.
Go back. So it's some kind of like neighborhood thingy. Okay, and then back
there.
U is the support of the mono. How is U the support of a monomial?
Well, think of
monomial
M to the
idea?
D as monomials, right? Just think.
N to the D, each vector gives you the vector of exponents of a monomial in D variables.
But the order matters in the two.
And so the order in the MD as a partial order corresponds to divisibility.
Oh, right, because you have X1 is the first element of the two.
Right, so your minimum one things are going to be generating your ideal.
Yes,
in the sense of algebra.
Okay.
That's why I kept bringing up syzygies and relations earlier, because once you shift to the algebraic viewpoint to the monomial ideal,
that's when
the things meet, you'll have a relation there, because it's not going to be free necessarily. You have, if there's not a relation, your rank goes up when they overlap.
So that's what I was going to check. So we said Betty number here, you meant in the sense of syzygies and that Hilbert polynomial.
I believe so, yeah.
In that sense.
Yes.
Using the word Betty number in that sense. Okay.
Syzygies, yeah.
Okay.
I view as the union of the support of the U.
Yeah, so sorry, so for those who aren't familiar, what we're saying is when you have your your ideals, you have relation. It's a commuter. We're in a commutative algebra. We can have relations. We have relations between the relations, and then that gives us a homology, and that's where you get these Betty numbers from. So you basically count how many relations between the relations, etc. Higher.
How am I
getting
getting
a minimal resolution of your diagram essentially, and
Sorry, how am I getting the monomial ideal exactly?
So let's draw a picture.
Yeah.
And I don't know if this will be visible.
You can erase it.
You can erase anything, I believe.
Okay, I'm just more worried about if people
Here's
are watching.
an eraser.
I don't know if I can like make them see this, so I apologize.
There's- Yeah,
it's a joke.
they see, I see your back on the screen.
Is there a place on, I guess if I write over here.
In fact, yeah. So you want.
Okay, so let's look at the two parameter case because it's easiest to draw pictures here. So say I have, let's draw a grid. So these are elements that are not present, and these are some elements that are present. Okay, this is my interval set. So I don't have this, I don't have this, I don't have this, I don't have.
Well, if you turn on the camera in that one.
Here, this one.
Okay.
Maybe choose a different color.
Okay.
So that's your cue.
Pull it out.
Yeah, so my Q is in white.
Okay.
Okay,
Okay.
so now,
Yeah, do this, sorry.
Now you take the
now I
upset.
take the upset of that.
Uh-huh.
Okay, and look at so the upset is like,
What's another one?
add these in that weren't there before. Right? Sorry, this is a bit tedious, making.
Two more to go.
Okay, and it goes on forever, right? And then I take its initial
Here's a yellow
scale,
one for you.
and so that consists of these. And so what does this have to do with monomials, I think was the question.
How are you building the monomial ideal?
Well, so here you have a monomial
Points.
one, here you have one x, here you have one y. Sorry, x squared. You have x cubed, and here you have
Why?
y cubed.
Square.
And over here you have x squared y. So the monomial, I think it's called U bar on my slide, would be y
squared.
X cubed y, right? Because the generators, it's like you basically look where the minima are, and those indices are going to be the exponents of your generating monomials.
I see. Thank you.
Yeah,
That makes a lot of sense.
again, we're saying that being less than means the monomials divide. One was a multiple of the other one.
Did I just see the slide again?
Yes, of course. If I can figure out.
So down the
Yeah.
So, but the point is, like monomial ideals, like there's a lot of algebraic questions that get asked about them.
Yeah.
But combinatorially, they're just upsets
Yeah.
in n to the
Yeah.
d.
I've never
That's all
thought
they
of it
are.
like that. Yeah.
So that's why when somebody thinks about this, they expect that monomial ideals could be relevant, as you immediately saw.
Yeah.
Quicker than we did, I might add, by far.
And that gives
It
balance.
was present already in Summerody and Kalsa. They have a whole section in the first multi-parameter paper
Yeah,
devoted to the connection to the Tor functor, which is how you get to these Betty numbers that describe the growth of the monomial ideals.
There's a Tor statement for the Posets.
there's a Tor definition of Betty numbers.
Well,
I think really
yeah.
the substance is this Hodges formula, which like you can find it in Miller and Sternfeld's book on combinatorial commutative algebra in like the first chapter. This is what says that like the combinatorial, like the connectivity of downsets is going to like.
It's the Betty numbers are determined by the sum of all the subcomplexes. That one? Or am I thinking of something else?
I don't know if that statement is equivalent.
Because you take the Stanley-Reisner ring of a simplicial complex, and then that has the Betty numbers, and then the Betty numbers are determined in terms of the homology of the subcomplexes.
So
Maybe this is a different.
Yeah, probably. I mean, there's also variants of this, and there's a dual variant, and it might be stated in terms of the Stanley-Reisner ring. I know just enough of this to apply Austria's formula here. But yeah. Now might be a nice time to state that formula for you, but I'm not going to because I don't remember it off the top of my head. Sorry.
Well, in rough terms, what does the formula about?
It expresses the Betty numbers of a monomial ideal in terms of the Betty numbers of a certain simplicial complex.
Okay, thanks.
And it's like in our case, when you're looking at first Betty numbers, you're just looking at the connectivity of something. And it's pretty much the same as, you know, the connectivity of these downsets.
Oh, that is what I said then. Because the Stanley reasoning ring, every Stanley reasoning ring comes from, or any monomial ideal comes from a simplicial complex, and then the Betty numbers of that are determined by the Betty numbers of the subcomplexes, which is, I think we just.
Yeah.
kind of
Okay,
just-
I can believe it's the same. I'm sorry, I'm no expert on that aspect. But okay.
Thank you so much, sorry.
Any other questions? Well, let's thank our speaker again. And, very interesting stuff. Thank you. Thank you.
Yeah, thank you. You guys actually were a really great audience. You're so active and
We asked a lot of questions.
Yeah, so that made it really fun.
Yeah, we found what you have to say interesting.
Thank you.